All right, so today we are doing Lewis structures 2.0, right? We're taking Lewis structures and we're elaborating on it. So what is the main problem with Lewis structure? The primary problem with Lewis structures is that they are flat. They don't give us any sort of information about what a 3D shape looks like. Just like if I take a picture of me, right? That does not represent my 3D shape. It represents my one-dimensional, two-dimensional shape, right? It represents me in a flat way, but it doesn't give you any sort of idea about depth or anything like that. Just like if you are shopping for a new car, and you look at pictures of the car online, and then you go see it, and it looks nothing like the picture you saw online, right? Flat versus 3 dimensions. Okay, we chemists are very, very, very interested in 3-dimensional shape. Very interested. The other main problem with Lewis structures is, remember I told you on Monday, when did you do Lewis structures? Friday, right? You could draw out shape like a T or shape like this, and I don't care about it right now, right? We're going to get into the actual nuts and bolts of what a molecule looks like in 3 dimensions. And so the other big problem with Lewis structures is that they don't take into account the massive amount of space that a lone pair occupies. Okay? When we drew an extra pair of electrons just sitting on the central atom, the way you draw that, it looks like they're just sitting there and they're not taking up any space. But that's not true. Okay? VSEPR stands for valence shell electron pair repulsion. Repulsion being the key word. Okay? That electron density in lone pairs and in bonds, they repulse each other. They want to be as far away from each other as geometrically possible. That's one of the big driving factors into 3-dimensional shape. And when you've got a lone pair of electrons just sitting there on the central atom in a Lewis structure, that doesn't factor in the fact that a lone pair is humongous, right? It takes up a lot of space. All that electron density alters the orientation of all the other bonds. Okay, so when we draw a Lewis structure, it's a good starting place, but it's not an accurate representation of what the 3D shape looks like. And so why do we care about 3D shape? Well, everyone in this room, based on what your majors are, should care about it to some extent, okay? Because how a molecule reacts, its reactivity specifically, its interaction with proteins, its interaction with other molecules, interfacing and all that great stuff, right? That's all a direct result of 3-dimensional shape. Okay, if you're looking at a protein, for instance, and you're looking at the active site, and the molecule that binds to the active site, only one specific one might fit, and that 3-dimensional shape determines whether or not it fits. Okay, so not just MDs and pharmacists, but if you're an anesthesiologist, if you're a vet, if you're going to be a dentist, if you're going to be a farmer, you're going to care about this, okay? Because if you care about chemistry in any way, you care about shape of molecules. Now, whether you enjoy it is another question. So like I said, VSEPR stands for valence shell electron pair repulsion, and it gives us the 3-dimensional shape. I gave you a handout. Okay, we're going to be referring to this today, so keep it handy. So this is, I can't, require it. I'm not going to come to your house and be like, have you read it? But I strongly, strongly encourage you to read in your textbook pages 307 to 314. Obviously, I can't require it. I can't come to your house and enforce this or not. Ultimately, your choice. But I really strongly encourage you to read in your textbook about VSEPR theory, because VSEPR is very visual, okay? You have to visualize what things look like. I'm giving you a nice little handout here, but your textbook's got a lot of really good pictures, okay? So if you're a person who likes pictures and can remember pictures better than you can remember words, then reading about this in your textbook's really going to be beneficial for you, okay? So this is the handout. Now your textbook's handout looks a little bit different, but pretty similar. Now we've got 2 new vocab words to talk about right here on your handout. Electron domain geometry, EDG for short, and then molecular geometry. So EDG and MG. Now some books call it electron group arrangement. So if you're looking at things online, like online tutorials and stuff, and you see it called electron group arrangement, don't have a panic. It's the same thing as electron domain geometry, EDG, and molecular geometry. All right? So the electron domain geometry and the molecular geometry are the two things we're going to learn today. And this will help you do the pre-lab for tomorrow. If you've already tried to do the pre-lab and you went, whoa, all right? You either read ahead or you're going to know how to do it today. So the electron domain geometry is the number of things. I put things in quote marks. So what is a thing? It is a lone pair and a bond. Okay, so we're looking at the central atom. What is on the central atom? We're looking at both lone pairs and we're looking at bonds. Okay, so the electron domain geometry determines the parent shape of the molecule. So let's look at, let's just look on the back, for instance. Let's do trigonal bipyramidal. Everybody look at the back. Total electron domains. All right, so there's the central atom. This is the parent shape. All right, now we're going to take that parent shape, and from that general shape, we'll get our specific geometry. Okay, so the molecular geometry is the actual shape. So if this is the parent, if this is the family, this is your specific answer. Okay, so let's look at it. If there are 5 bonds and 0 lone pairs, right? So that means there are 5 bonds, all bonds, and none of them are lone pairs. Then the molecular geometry will be the same as the electron domain geometry. Trigonal bipyramidal, trigonal bipyramidal. Okay? If you're looking at the central atom and it's got 5 things, 4 of them are bonds, and 1 of them is a lone pair, it would be seesaw. Does everyone see how we got that? We're going to go through lots of examples. And look at the orientation of seesaw. Okay, look, that lone pair is on the equatorial position. In other words, it's back behind the page. That's protruding back behind the page. One of those bonds is coming out towards you. One of them's in the page, right? So that's the way to get the pair of electrons furthest away from everybody as possible. That's why it looks like a little seesaw, right? You can imagine like a seesaw, the legs, and then there's the seesaw going up and down. Right? So imagine that rotation. If you've got 5 domains, 3 of them are bonds, 2 of them are lone pairs, that would give you T-shape. Again, we're trying to get those lone pairs as far away from each other and as far away from the bonds as possible. And then if you have 5 total domains, 2 bonds, 3 lone pairs, all 3 of those are on the equatorial position, and now it's linear. Okay? We want to get those lone pairs as far away from each other as possible. Okay, so the final molecular geometry looks at the effect of those lone pairs and what does that do to the shape. And if there are no lone pairs, then the electron domain and the molecular geometry are the same by definition. Okay, because if there are no lone pairs, there's no change. So the best way to get good at this is just practice. So let's go through some examples. We're going to do these 3 simultaneously. All right, if I said draw the Lewis structure for ammonia, methane, and water, this is what you'd give me, right? I hope. You've got 8 valence electrons, 8 valence electrons, 8 valence electrons, right? So they all have the same number of valence electrons. Their Lewis structures do look different though, right? 1 carbon atom with 4 bonds, excuse me. Nitrogen with 3 bonds and a lone pair, 2 bonds and 2 lone pairs. So let's go through and figure out their electron domain and molecular geometries. So we look at the central atom. We're only looking at the central atom. What's on the central atom? Carbon's got 4 bonds, no lone pairs, 4 total things, right? Central atom's got 3 bonds and 1 lone pair, 4 total things, right? This one's got 2 bonds, 2 lone pairs and 2 bonds, 4 total things. So they all 3 have the same parent shape. They all 3 have the same electron domain geometry. What is it? Look at your sheet. What's the scenario where you've got 4 things? Tetrahedral, right. So they're all tetrahedral, right? As the electron domain geometry. They're tetrahedral. Does this make sense? Because you've got 4 things, right? 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4, right? So 4, 4, 4. The parent shape comes from the number of things. And by thing, I mean bond and lone pair. Okay, I know thing is not a very scientific word, but it works. Now let's look at the molecular geometry. So there's our central atom again. We have no lone pairs. So everybody look at your handout. What's the scenario when you've got 4 bonds and no lone pairs? What's the shape of the molecular geometry? It's what? Tetrahedral, right. When there's no lone pairs, the molecular geometry and the electron domain are the same. So this is tetrahedral. What is NH3? What will its molecular geometry be? 3 bonds, 1 lone pair. Trigonal pyramidal. Right, good. All right, this lone pair is up here occupying space away from the rest of the bonds. Good job. And then in number 4, 2 bonds, number 4. For 4 domains, 2 bonds, 2 non-bonding, what would that give us? Bent. Good. So all 3 of these have the same electron domain geometry. What makes them different is their molecular geometry, which comes from the number of lone pairs. Okay? If there are no lone pairs, the molecular and the electron domain are the same. If there's 1 lone pair, or if there are 2, right, that's what determines the molecular geometry. And again, these pairs are furthest away from each other as they can be. Okay? This is behind the screen. This one's coming out of the screen. And so tomorrow in lab, we're going to be breaking out the model kits, and you're going to be making these models so you can see it, right? Because even this is still flat. Seeing it in real life, 3-dimensional, that's what's going to help, I think, make it cement. All right, so they all have the same electron domain. What makes them different is the number of lone pairs. Does this make sense? Yes? So first step, you have to draw a Lewis structure, right? Look at the central atom, and then you can figure out electron domain and molecular geometry from that. This is actually a topic that students do awesome on the exam. Like this is what the test. Now, I want to note something really important here. If you've got a double bond, that counts as 1 thing. Okay, that doesn't count as 2 things, it counts as 1. Okay, just like if you have twins, that counts as 1 pregnancy, not 2, right? You've got 2 pairs of electrons being shared between the same 2 nuclei. Okay, so that and a triple bond would count as 1 thing too. Okay, just counts as 1 thing. All right, let's do this one together. So first thing we got to do is we got to draw the Lewis structure. So I'll give you the Lewis structure. Now we talked about this on Monday, right? Any one of these, there are 2 other resonance structures, right? You can have the double bond here, you can have the double bond here. All 3 of them are equally favored. So there's nothing to worry about which resonance structure. Now we're going to look at the central atom. So just that sulfur. How many things are on the central atom? 3, right? 1, 2, 3. Remember, a double bond counts as 1. Double bond counts as 1. So 3 things on the central atom. Okay, let's look at our handout. What is the electron domain geometry? Trigonal planar, right? Planar means flat, by the way. Okay, planar means flat, like this piece of paper is flat. Okay, trigonal planar. So that's the electron domain geometry. So there's the electron domain geometry. So what would the molecular geometry be for this one? Do we have any lone pairs? No. So electron domain and molecular geometry are both trigonal planar. If I asked you, is this a flat molecule, would your answer be yes? Yes, it's flat. Planar means flat. Okay, that's a flat molecule. Does this make sense? All right, so there's our final answer. Okay, let's do PCl3. So there's the Lewis structure. Now again, this is why Lewis structures give us a really incomplete picture, because the way this is drawn, it appears that this lone pair isn't taking up very much space. But in reality, it's taking up a lot of space, right? Because that electron density is repulsing all this electron density. They don't want to be around each other, right? They want to be as far away from each other as they can. So this is why Lewis structures don't give us the full picture. So we look at the central atom, which is that phosphorus. So how many things are on the phosphorus? 4, right? 1, 2, 3, 4. That lone pair counts. So we've got 3 bonds, 1 lone pair. Now we just look at our chart. If we have 4 things, that gives us tetrahedral. But because it's 4 things, but 1 lone pair, that gives us trigonal pyramidal. This lone pair is up here, away from the rest of the bonds. So if I asked you what's the molecular geometry, this will be your final answer. I'm not going to want the electron domain geometry unless. All right, let's go over carbonate. So first I have to know the formula, right? What's the formula for carbonate? CO3, 2 minus, right? So there's our Lewis structure, equally favored, right? You could have a double bond on the right, on the left, or up and down. They're all equally favored from formal charge. So there's our Lewis structure. We look at the central atom, right? We've got 3 bonds. One of them happens to be a double bond, but that double bond only counts as 1, right? Just remember that only counts as 1. We don't have any lone pairs. So that leads us to then go to our handout. Is everyone with me so far? All right. So no lone pairs means that the electron domain and the molecular geometries are the same. So this is trigonal planar. So is this molecule flat? Yes, it's flat. Planar means flat. Questions on this one? If you made a mistake, do you see where you made it? There's our final answer. Okay, you do this one. Chlorate. Do the chlorate ion. I'm going to pause the recording again. Let's go over chlorate. What's the formula for chlorate? ClO3 minus, right? So there's the Lewis structure. Do we agree? So we've got 3 bonds, 1 lone pair. So are the electron domain and molecular geometry is going to be the same? No, that lone pair is going to change the electron domain and molecular geometry. So the electron domain geometry would be tetrahedral, because there are 4 things, right? 3 bonds, 1 lone pair. But because of that lone pair, the molecular geometry becomes trigonal pyramidal. Does this make sense? Makes sense? Makes sense? If you made a mistake, do you see where you made it? All right, so there's our final answer. Okay, do tetrachloroiodate, which is ICl4 minus. ICl4 minus. I'll pause the recording for this one. Okay, let's go over this one. So I gave you the formula, so nothing to worry about in that department. There's the Lewis structure. Do we agree? 2 lone pairs on the central atom. This is why you will get in trouble, molecular geometry-wise, if you take a lone pair and instead of putting them on the central atom, you make a double bond out of it, right? That will really mess things up. Extra electrons go on the central atom. So in this case, we've got 4 bonds and 2 lone pairs on my central atom. Right? We've got 4 bonds, each with the chlorine, plus we've got those 2 lone pairs. So the electron domain geometry is based on 6, right? It's based on 6, which on your handout, if you look, refers to octahedral. Octahedral. So there's the electron domain geometry. It's octahedral. Right? These 2 are coming out of the board. These are going behind. And these are above and below this plane here. Okay, because we've got 2 lone pairs, what is the shape of the molecule? Square planar, right. So here those lone pairs are on these axial positions above and below getting as far away from each other and as far away from the electron density in those bonds as possible. So is this molecule flat? Yes, planar means flat. So there's our final answer, square planar. All right, do PCl5. Pause the camera. PCl5 is a Lewis structure we've already drawn. We did it on Friday. No lone pairs, correct? 5 bonds, no lone pairs. So the central atom, based on that information, will have, the molecule have the same electron domain and molecular geometry, correct? Because there are no lone pairs. So this is both going to be trigonal bipyramidal. This is the arrangement that gets 5 bonds as far away from each other in space. Okay, because those bonds repel each other. Trigonal bipyramidal. All right, last one, triiodide, which is I3 minus. Triiodide, which is I3 minus. Take a second to jot it down, and then I'll pause the camera. Okay, last problem. Triiodide, I3 minus, has a Lewis structure that you wouldn't expect, right? If you just look at that, what's unique about this Lewis structure? How many lone pairs do you have on the central atom? You got 3 lone pairs, right? We haven't encountered any so far yet this semester with 3 lone pairs. So I think this is the first problem you've done with 3 lone pairs on the central atom. Right? Do we agree on the Lewis structure? 3 times 7 is 21, plus 1 is 22. So all those extra lone pairs go on the central atom. Central atom's got 2 bonds and 3 lone pairs. Do we agree? So based on that 5 domains, that leads us to which parent shape? Trigonal bipyramidal, right. So the electron domain geometry is trigonal bipyramidal, but because of those 3 lone pairs here on the equator, right? Those 3 lone pairs want to be as far away from each other and from other bonds as possible. So this is actually a linear molecule. Any questions on this one? Okay, that's where we're going to stop for today. Don't forget that tomorrow you still have pre-lab.